Swayam Prabha. Digital India. Educated India.
In this lecture, we are going to discuss the first law of thermodynamics. Thermodynamics may appear to be a mathematical science because there are so many equations that we have to deal with, but actually the laws of thermodynamics are based on several experimental observations. And one such experimental observation is that heat and work are equivalent ways of changing the internal energy of a system. Change in internal energy of a system we are writing as delta U. So, what I am saying is that heat and work are equivalent ways of changing the internal energy. Whether we heat the system or we do work on it, the internal energy of the system is changing or increasing, and the system is blind to it, that how the energy is being given to it. It is like taking an example of, let us say, if we consider Q and W as, let us say, 500 rupees currency note or 1000 rupees currency note, and we go to a bank and deposit, the statement that we get is that the total amount deposited in the bank, irrespective of recognizing whether you have deposited 500 rupees note or 1000 rupees notes or 2000 rupees notes. So, in the same way, the system is blind to what is coming, whether the energy is flowing in the form of heat or work, but it is leading to change in internal energy of the system. So, if I write in a formal way, delta U is equal to Q plus W. This is the formal statement of the first law of thermodynamics. This is a mathematical statement of first law of thermodynamics. And as we will see that this is a very useful mathematical equation. And then, as we discussed in the previous lecture, that we can express the internal energy changes as well as the heat in the form of work, and that is what I mentioned, that work is the most fundamental quantity in thermodynamics. And today I will demonstrate that we can express the change in internal energy exclusively in terms of work and the heat also in terms of work. So, the equation that we just derived is delta U is equal to Q plus W. And let me consider a process which is adiabatic. Adiabatic process means Q is equal to 0. So, I will write now delta U is equal to W adiabatic. Remember that we have discussed that work is a path function, but see what we are doing here is we are connecting a path function with a property which is a state function. A path function is becoming equal to difference in the properties of which is a state function. That means, according to this equation, the work done in changing a system from one specified state to another specified state under adiabatic condition is going to be same irrespective of how the work is done. Let us take an example. Let us say I take 5 kg of water and we need to change the temperature of water by some amount. And if we keep adiabatic conditions, then the work required to change this temperature will be same whether this work is done in a mechanical form, that is by stirring it with the pedals or by passing an electric current. The same amount of work will be required. And this forms an alternate statement of the first law of thermodynamics, that is the work needed to change an adiabatic system from one specified state to another specified state is the same however the work is done. And internal energy being a state property, the change in internal energy now we have connected with work and hence demonstrating that the internal energy or the change in internal energy can be exclusively written in the form of work, and work is something which we can actually see with our eyes being happening. You remember that earlier I discussed that work is said to be done in a process if that process can lead to change in height of a weight somewhere in the surroundings. So, that we can actually see with our eyes. Now, after having demonstrated this connection between delta U and W, now I will demonstrate that we can also express heat exclusively in terms of work. Here we have taken an example of an insulated system, that is which does not allow the transfer of heat as forming the adiabatic process. Now, let us assume that we just remove the insulation, and once we remove the insulation, that means now if the work is done on the system, then some of that work energy can leave the system in the form of some form of energy, and we usually call that energy as heat. So, therefore, earlier we had work under adiabatic conditions, and now if we remove the insulation, let us say the new work is W. To get the same change, then this difference in the work is equal to energy that has left the system, and that energy is heat. Because now the system is not adiabatic, insulation is not there, therefore, some amount of the work done on the system can actually leave the system in the form of some form of energy which is called heat. So, if the initial and final states are same, then this difference in the work done is equal to heat, and from the previous discussion W adiabatic we just discussed that it is equal to delta U, and if I rearrange this I get the first law of thermodynamics back. from an alternate discussion. Now, let us take a look at this slide. The delta U will be W adiabatic minus Q, and since W adiabatic is equal to delta U, therefore, Q is equal to delta U minus W, or delta U is equal to Q plus W. This is what I just described, and this is for a finite change. Delta U is equal to Q plus W is for finite change, and for infinitesimally small changes I can simply write du is equal to dq plus dw, and this is another equation which will be very useful when we deal with the infinitesimally small changes and then derive several other equations. But the point to recognize here is this equation, that we have demonstrated that we can express heat exclusively in terms of work. So, therefore, once again I re-emphasize that work is the most fundamental quantity. Both the internal energy, changes in internal energy, and heat can be expressed in terms of work. Let us recall now the first law, du is equal to dq plus dw, where dw represents the work done. The work done can be of two types. First one is the known pressure volume work, which in some books you will see that they write as extra work. And the second type of work is the work of expansion, which is also called the pressure volume work. Okay. Now, suppose if we do not allow the system to do any extra work, if no known pressure volume work is done, and if the volume is held constant, that means there will be no pressure volume work also done. What I am trying to say is that we have du is equal to dq plus dw, and if we do not draw any work from the system, that is, the system is not allowed to do any non pressure volume work or pressure volume work. Pressure volume work will be 0 when the volume is held constant, and if there is also no extra work, then du will become equal to dq, and what are the constraints? The constraints are constant volume, and the other is no extra work. So, let us now take a look at the slides. That du is equal to dq plus dw, as I mentioned above, it is pressure volume work or non pressure volume work, and in case there is no work done, whether it is of pressure volume work or non pressure volume type, then du is equal to dq. And for a finite change, what you need to do is just integrate, and what you have delta u is equal to QV. The heat supplied to a system at constant volume is equal to change in its internal energy. So, experimentally if we want to determine the change in internal energy, one way of finding it out is by measuring the heat supplied to system provided the volume is kept constant. Now, let us discuss enthalpy. Suppose if the volume is not held constant, you allow the system to expand or compress, let us say expansion. We can consider pressure constant, but let the volume change. Now, the amount of heat supplied is no more equal to change in its internal energy, it is a different quantity now, because some of the heat supplied can be used to drive back the surroundings. And we will see here that if the pressure is held constant, then the amount of heat supplied turns out to be equal to change in enthalpy. Let us see how it comes. How do we define enthalpy? It is a very common question asked in several interviews, and sometimes there is a confusion in the definition of enthalpy, and let us get rid of that confusion. Enthalpy, how do you define enthalpy? The definition of enthalpy is H is equal to U plus PV, where U is internal energy of the system, P is pressure of the system, and V is the volume of the system. The confusion sometimes can come because of this PV term, because PV is equal to nRT is generally used for ideal gases. But remember here that this PV is a part of the definition. This definition applies to all the systems, irrespective of what is the state of the system. So, not to be confused with the ideal gases. The definition of enthalpy is H is equal to U plus PV. All right. Now, let us say there is some advancement of the process. The change dH is going to be equal to du plus PdV plus VdP. So, dH is equal to du by first law is equal to dq plus dw. This comes from du, then plus PdV plus VdP. Now, let us consider mechanical equilibrium between system and surrounding. So, then this equation becomes dq. If there is a mechanical equilibrium between system and surrounding, I can write dw as minus PdV, as we discussed in the previous lecture, that dw is equal to minus PdV in case there is a mechanical equilibrium between the system and surrounding, and also there is no other work done, that is known pressure volume work also is equal to 0. So, in that case this equation becomes of this form, this and this cancel, and if pressure is held fixed, then dH becomes equal to dq at constant pressure, and also the condition is that there is no extra work or other work or whatever way you want to call it. And that is what is seen in the slide. that dH is equal to dQ at constant pressure, no additional work. And for a finite change, when you integrate it, delta H is equal to Qp. Okay. So, the things to remember are that if we are interested in measuring delta U, this will be equal to Qv, and delta H, this will be equal to Qp. Here the volume is held constant, here the pressure is held constant, and in both the cases there is no additional work done. And later on we will discuss that how to experimentally determine what kind of calorimeters are required to measure the values of delta U and the values of delta H. Now we will discuss another very important thermodynamic quantity, and it is called the heat capacity. What is heat capacity? The definition of heat capacity is the amount of heat required to change the temperature of a system by 1 Kelvin. And obviously, if the temperature of the system is to be changed, it will definitely depend upon the conditions, that is whether the pressure is held constant or the volume is held constant. So, therefore, we will discuss two types of heat capacities. One is the heat capacity at constant volume. The heat capacity at constant volume Cv is defined as the partial derivative dou q by dou t at constant volume. The amount of heat required to change the temperature of a system by unit at constant volume. And from this equation, I can write that dq is equal to Cv dt at constant volume, and we have just shown that dq at constant volume is equal to du is equal to Cv dt, and what is the constraint? You have constant volume. If the volume is held constant and the temperature is changed, we can straight away use this equation du is equal to Cv dt. However, as we will show later on, that for a perfect gas, for an ideal gas, this equation always applies irrespective of whether the volume is held constant or not. That we will discuss later. Let us take a look at the slide. The heat capacity at constant volume is defined as Cv is equal to dou u by dou t at constant volume, because dq at constant volume is equal to du. Therefore, dou q by dou t at constant volume becomes du by dt, or dou u by dou t at constant volume. Take a look at the figure. The internal energy is temperature dependent, and usually the internal energy is varying with temperature in a non-linear fashion. And we can see that the slopes of the curve at point P and at point Q are different, and the slope of the curve is equal to dou u by dou t at constant volume. This represents the heat capacity at constant volume. That means, the heat capacity at constant volume for this system at point P, where the temperature is certain value, is different than the heat capacity at another temperature. Note that heat capacity is the definition, by definition it is a partial derivative. It is a partial derivative because one of the variable you are keeping constant, that is volume is held constant. Heat capacity is an extensive property because the amount of heat required to change the temperature by unit degree will depend upon the size. However, if you calculate per mole, the molar heat capacity will become intensive property because you will be defining it as per mole. As I just discussed that the CV is temperature dependent generally. The CV at point Q is greater than CV at point P unless the temperature range is very small, then it may be considered constant. We just discussed that du is equal to CV dt always if the temperature, if the volume is held constant, and for finite change, and if you take the integrated form of this, you can calculate delta u, and delta u will be equal to CV times delta t. This is at constant volume. Now, let us discuss the heat capacity at constant pressure. Now, if the pressure is held constant, then definitely now the amount of heat required to change the temperature by 1 degree will be different. And how we define? Cp, this is heat capacity at constant pressure, this is equal to dou q by dou t at constant pressure, and since we just discussed that the heat at constant pressure is equal to the change in enthalpy. So, I will write this as dou h by dou t at constant pressure. Writing this in another form, dH is equal to Cp dt, again I will write as constant pressure. And for a finite change, delta H is equal to Cp times delta T if Cp is not depending upon temperature, otherwise the temperature dependence has to be accounted for, we will discuss later. So, here again this equation dH is equal to Cp dt at constant pressure is always applicable as long as you hold the pressure constant. However, again we will demonstrate later on that if you are applying this to perfect gas, then this always holds true for perfect gas. You do not have to hold the pressure constant, then this equation can be straight away used for perfect gas. Let us take a look at the slides where we define the heat capacity Cph dou h by dou t at constant pressure, and if you look at the figure, enthalpy is also temperature dependent, but generally the enthalpy varies more sharply compared to internal energy, and this is because now you are holding the pressure constant. Earlier we were holding the volume constant when we were discussing the Cv, that heat capacity at constant volume. and if you hold the pressure constant, then some of the energy can be used as to do work, and therefore, one may require more heat to change the temperature by a unit degree. So, therefore, the slope of H versus T is going to be higher than the slope of U versus T. That is, the value of Cp in general is greater than the value of Cv. Here again, please note that it is a partial derivative. Heat capacity is an extensive property, molar heat capacity is an internal intensive property, and the final point to note that Cp is greater than Cv, because you can see here at the points P or point Q in the figure, the slopes are different, and the slope corresponding to the plot of H versus T is higher than the slope corresponding to U versus T. Therefore, Cp m is greater than Cvm. What are the advantages of Cp and Cv? There are many applications of Cp and Cv. Let me first discuss the temperature dependence of reaction enthalpies. It is a very useful thermodynamic quantity which will allow connecting one thermodynamic property to another at different temperature without doing additional experiment. So, look at this definition: Cp is equal to dou H by dou T at constant pressure. So, dH is equal to Cp dt. I am assuming that the pressure is constant, right. So, this is H at Ti, and let us say the final limit H as Tf, and we have Ti to Tf, fine. So, H at Tf is equal to H at Ti plus integration Ti to Tf Cp dt. Now, depending upon whether the heat capacity at constant pressure is temperature dependent or not, it can be either taken out of integral or the appropriate expression can be used. Usually, the heat capacity Cp for a very narrow range of temperature can be considered as temperature independent, and very safely and very accurately it can be taken for an ideal gas. For a small range of temperature, Cp usually does not depend upon temperature. In that case, it can be taken out of integral. But in any case, if the temperature range is small, then to a fairly good level of accuracy, heat capacities can be considered independent of temperature. Otherwise, an appropriate equation should be used. Let us take a look at the slide. In case the heat capacity is not independent of temperature, then a convenient expression, it is again an experimental observation, that molar heat capacity Cpm usually varies with temperature according to A plus B T plus C by T square, where A, B and C are empirical constants. From the definition of Cp, as I just discussed with you, the temperature dependence of enthalpy can be written, and if I apply this to the changes under standard state conditions, I can introduce deltas, and this forms the Kirchhoff's law. Very important, it connects the reaction enthalpy at one temperature with the reaction enthalpy at another temperature. What you need is the information on the values of heat capacities. Delta Cp, which is the change in heat capacity when the reaction proceeds. Either one can experimentally determine it or one can calculate it if you know the heat capacities of the products and reactants. Then by using the suitable stoichiometric numbers, the difference in heat capacities of product and reactants will give you the value of delta Cp. So, finally, as I said that Cp and Cv are very important thermodynamic quantities. How do we generally interpret heat capacity? The general definition, that is the amount of heat required to change the temperature by 1 Kelvin. And if we think a little bit deeper, that the amount of heat required to change the temperature of a system will definitely depend upon the type of system. It will depend upon the structural rigidity of the system, because if the system is very rigid, if there is a very strong bonding in a particular substance, then to raise the temperature by 1 Kelvin, a lot of heat will be required. So, I can write in general that Cp of a rigid system will be higher than the Cp of a soft system. In the design of materials, for example, Cp, which is defined as, or Cp or Cv, which is defined as dou Q by dou T at constant pressure. If upon supplying the heat, the change in temperature is very little, then the heat capacity is very high. If that is what we want some material which should not respond to heat supplied to it in terms of large changes in temperature, then you want a high heat capacity material. That is, in that case, the heat supplied will not lead to a reasonable changes in temperature. However, if heat capacity, for heat capacity to be very low, the amount of heat supplied will lead to larger changes in temperature. So, if we want a system which should immediately respond to the heats, which should, a small application of heat should lead to large changes in the temperature or large large change in the temperature of the system to which the heat is supplied, then the heat capacity is going to be very low. Phase transitions. Again, if we look at this definition, a phase transition can be, let us say, if I just took water, liquid to water, vapor at 100 degrees Celsius and 1 atmosphere. Let us say P is equal to 1 atmosphere and temperature is equal to 100 degrees Celsius. This is a phase transition. At phase transition, the heat capacity becomes infinite, because whatever is the heat supplied to the system at phase transition, that is used to drive the endothermic phase transition. It does not change the temperature. That is why the phase transitions are accompanied with infinite heat capacity values. And another important information that comes out of these values of heat capacities is on intermolecular interactions. A detailed discussion will require a long time, but to explain very briefly that any structural rearrangements as a result of intermolecular interactions should be reflected in the values of Cp and Cv, because after all Cp and Cv depends upon the rigidity of the system, the nature of bonding, and if the intermolecular interactions are leading to alteration in the nature of interactions, nature of bonding, then Cp and Cv should respond to it. So, therefore, Cp and Cv are very important thermodynamic quantities which can be used to get a lot of information and which has lot of applications. And as I just discussed as one example using Kirchhoff's equation, that it is a connector of thermodynamic quantities at different temperatures. So, I hope that the first law of thermodynamics, which describes the changes in internal energy in terms of heat and work, is very clear, and the various equations which we developed have lot of applications which we will discuss in the tutorial session. Thank you very much.